This is part 2 of our lesson about making correct measurements. Of course, measuring things is important in science. We're going to do it quite often, and we want to do it the right way. So in part 1, we talked about a very simple statement that tells us how to do that. Here it is. When we're making a correct measurement, no matter what kind of device we're using all the marks on the measuring device, and then we're estimating one more digit. Why are we doing that? We want to get as much information as we possibly can from whatever we're using, whatever equipment we're using, but we don't want to be making things up. We don't want to report more information than is really there. That's why we have to use the equipment correctly. So we talked about a graduated cylinder in the first part of this lesson, in the first video. In this video, we're going to talk about some other equipment, including balances. So here's a picture of a 4-beam balance. Here's an actual 4-beam balance in my hand, same kind of thing that's in the picture. And this is a 4-beam balance because it has 4 beams or bars, and each one has a sliding weight on it. You probably used a balance like this before in science class. You put something on the pan, you slide the weights until the balance is level, and then you read the numbers that the weights are pointing to, add them together, and it gives us the mass of whatever is on the pan. And the challenge is getting the correct number from the beam that has the smallest numbers on it. So here's a close-up of that smallest beam from a 4-beam balance. And we can see that there's a sliding weight, and it's pointing to a number somewhere between 0.1 and 0.2. Now, a balance like this is measuring things in grams. So the 0.1 refers to 0.1 grams, and the 0.2 refers to 0.2 grams. And we can see that there are some marks between 0.1 and 0.2. So we can count the number of steps from 0.1 to 0.2, and we can see that each one of these marks stands for 1/100th of a gram. So here's a 0.11, 0.12, 0.13, 0.14, and we can see that our weight is pointing to a number between 0.16 grams and 0.17 grams. But it's not pointing to exactly either one of those. So in order to report our measurement from this balance, we're not going to write down either one of these things. We're going to estimate one more digit. We're going to estimate one more digit. So I think that this weight is closer to 1.7 than it is to 1.6. So I'm going to estimate that it is 0.166 grams, and this last 6 here is the estimated number. The marks on the balance tell me that this mass is at least 0.16 grams, and I estimate that final digit to tell people that it's a little more than 0.16, but it's not all the way to 0.17. Use the marks, then estimate. Let's try again. Here's another balance. Here's the smallest beam, or the beam with the lowest numbers on it. This weight is pointing to somewhere between 0.3 and 0.4 grams, and these are grams again. G is the abbreviation for grams. The marks, each mark is for 1/100th of a gram, so the weight is actually pointing to a place between 0.32 and 0.33. It's not either one of those. It's not exactly 0.33, and it's not exactly 0.32. So that's not what I'm going to write down. I'm going to estimate that this is slightly closer to 0.33 than to 0.32. So I'm going to write down 0.327 grams. The 7 is the number that I estimated. The marks on the balance tell me that it's at least 0.32 grams, and then I estimate how much more it is, and that tells the reader that it's more than 0.32, but it's not all the way to 0.33. Okay? I use the marks, then estimate it. So we might come across another type of balance called a triple beam balance. Triple, of course, means 3. Here's, oops, that's not the right balance. The triple beam balance looks like the one in the picture here. Here's an actual triple beam balance in my hands. Looks a little bit different. We'll use this if we need to weigh something that's too heavy for the 4-beam balance. It has 1, 2, 3 beams or bars, each with a sliding weight. Put something on the pan, slide the weights to level the balance out, add up the numbers to get the mass. And again, the challenge is going to be to get the correct number from the beam with the smallest numbers. So here's a close-up of an example. Our sliding weight, which is right here, is pointing to a place between 1 and 2 grams. And the triple beam balance is different. So the smallest numbers on it are whole grams. Each one of the marks in between is 1/10 of a gram. So we can see that this weight is pointing somewhere between 1.3 grams and 1.4 grams, but it's not pointing to exactly either one of those places. So that's not what we're going to write down. We're going to estimate one more digit, and we're going to say that this is 1.37 grams. My estimate for the last digit is a 7. Your estimate might be something different. Somebody else who's reading it might be slightly different. But I'm telling someone who looks at this measurement that the marks on my equipment tell me that this piece, whatever we're weighing, this weight pointed to 1.3 grams plus a little bit more, but it wasn't pointing to 1.4 grams. So it's somewhere between 1.3 and 1.4. And by looking at this, someone can tell that there was a mark for 1.3 and a mark for 1.4, and I estimated that last digit. Here's another example. Here's our sliding weight. It's not 5, it's not 6. It looks like it's right on 5.9. How will I tell readers that it's right on 5.9? I won't write down 5.9 grams. I will estimate one more digit, and since I don't think it's any more than 5.9, I'm going to write down 5.9 grams and estimate a 0. That's an estimate to tell people that I think it's pointing right to the mark for 5.9. Okay? So 5.9 comes from the marks. The 0 is the estimated number. Okay? Always use the marks to take you as far as you can and then estimate one more number. We will most often use an electronic balance. An electronic balance plugs in, and it's a lot easier to use, but it doesn't always have enough capacity. We'll use this whenever we can. Here's an actual electronic balance. And when we use the electronic balance, we want to be sure that we read all of the numbers from the balance. So in this case, we have a piece of orange plastic, and the display in the picture says 9.033 grams. Now, most of our electronic balances measure to the 1,000th place, and you will find that when you put something on the balance that this last number fluctuates a little bit. So you do have to estimate what that last number is. So even with the electronic balance, there is some judgment involved about what the mass of an object is. But you do want to use all of the digits from the display so that you get the maximum out of your piece of equipment. You get as precise a measurement as you can possibly make. Here's a little summary of the kinds of numbers we should come up with when we're using each one of our 3 kinds of balances. If we're using an electronic balance, we should get numbers that have 3 digits to the right of the decimal point. If we're using a 4-beam balance, the same thing, 3 digits to the right of the decimal point. But a triple beam balance won't do that. A triple beam balance can only give us 2 digits to the right of the decimal point. If we write down 3, we're making things up that just aren't there, and we're not making a correct measurement. So this same sort of technique applies to making measurements with a ruler. How long is this line? The line we're talking about is this green line that's underneath the transparent ruler. These measurements are in centimeters on this ruler. So these are centimeters, even though it doesn't say that. And you can see that our line is between 3 and 4 centimeters. Obviously this is magnified to put on the board here. Our line is between 3 and 4 centimeters long. We can count the marks and think about them, and we can figure out that each mark stands for 1/10 of a centimeter. So it's really between 3.7 and 3.8 centimeters. So in order to write a correct measurement from this ruler, I'm going to write down the 3.7 that I got from the mark, and then I'm going to estimate that it's halfway between the 3.7 and 3.8 mark. So I'm going to estimate this last digit to tell somebody who's reading this that this is at least 3.7 centimeters long. I think it's a little bit more than that, but I don't think it's all the way to 3.8. I used the marks and estimated one more digit. Even when we use a thermometer, we'll do the same thing. At home, you look at the thermometer and you say, oh, it's 70 degrees or 40 degrees, and that's good enough for you to make a decision about what to wear or whether to go out. But in science class, we want to get as much information as we can from the thermometer. We're going to find our thermometers are marked in 1 degree, in increments of 1 degree Celsius. And so when we read our temperatures, we're going to use the marks, and then we're going to estimate a digit in the tenths place. So use the marks, estimate one more digit. When we do that, we end up with measurements that have a certain number of figures in them. And the figures, or the digits, are called significant digits, or significant figures. Significant figures tell somebody who's looking at our measurements how we measured, what kind of equipment we used, and it also helps to tell us what we can do when we make calculations with our measurements. So here's an example of a measurement, 425 milliliters. This has 3 significant figures in it, and those significant figures, again, tell how we made the measurement and what we can do with that number when we do calculations. And some of you might hear more about that later on. So that's it. Not only do we want to measure things, but we want to do it correctly. Thanks for listening.